So one of the more important tools when dealing with forces is what's called a free body diagram. I have a system here. It's 3 cars that are being pulled across a level surface by some applied force. Once again, the idea of an applied force is just the force. We're not keeping track of exactly what's applying the force. It very well could be a tiny reindeer. It could be a UFO. It could be a couple of strongmen. It doesn't really matter to us. We just simply call it applied. Now, talking about this problem, I want to look at what forces are interacting with what cars and where and in what direction. Okay? So, what we need is we need a graphical way of representing all the forces that are acting on something. And that's called a free body diagram. Okay. The first law of a free body diagram is the free body diagram can only be referred to one body at a time. We don't take all 3 cars and start drawing arrows all over 3 cars. It just doesn't work that way. It's really difficult to keep track of things that way. So when doing a free body diagram, rule number 1 is you do one body at a time, one object at a time, one car at a time, one whatever at a time. Okay. So here's my car number 1. So, car number 1, I'm just going to write car number 1 over here. Now, we can say what forces are on car number 1. Well, the first one's obvious. It's the force applied. There's a big arrow pointing there saying force applied, force applied. Okay, so we have 1 already. Now, the second rule of free body diagram is that when we take the arrow, we put the arrow with the tail of it at the center of that object. Okay. When dealing with motion, most forces can be forces can be considered to be applied at the center of that object. Oh, excuse me. When we're dealing with torques, we have to be concerned about the distance that object is away from there. But for just forces, we consider the forces at the center. Okay? So the tail starts at the center. So here's the center of the object. And here's my force applied. I'm going to use blue to represent that force. So here's my force applied. It starts there, and then there's an arrow. Now remember, the length of that arrow should represent the strength of that force. If that force is small, it should be a short arrow. If it's large, it should be a big arrow. And then this is force applied. I'm just going to call it force AP. Let me make it a little bigger so everyone can see it. Okay? Now the next question you have to ask yourself is what other forces are in this system? Well, the next one should be hopefully obvious. Well, more than likely it's on the Earth, so there's a gravitational force acting on it. So gravitational force is pulling everything down towards the center of the Earth. So we already know the direction of it. So we're going to draw an arrow starting from the center down. Okay? Now force AP is representing the force of gravity. There's 2 ways in which we can represent the force of gravity. One is F with a G, like that, or mg. Okay, both will work. I use mg because it's a shortcut, but fg works just the same. Let me make sure that that g looks like a g and not a y. There we go. Now, what other forces? Well, there's another one that hopefully is kind of obvious. I've got 2 surfaces in contact with each other. That automatically means that there's a normal force. It doesn't automatically mean that there's a frictional force, but it definitely means that there's a normal force. Now, normal is always perpendicular to the surface. So, which way would the force have to be on that car to prevent it from falling through that surface? Well, it's up. And we just expressed normal as a big N. Okay? Cool? And then lastly, there's this chain or string or whatever that's pulling it back. This car is actually pulling that car back. So there's one last force in this direction, and that one's tension. Okay? That's a free body diagram. All the forces are represented. If there was a third or a fifth force, the force of friction, I can presume that the object, the force applied, is in this direction, so more than likely the force of friction would be in this direction. And that's how we would express it. Okay? Just bing, bang, boom. Done. Okay? Now, looking at car number 3, car number 2 we're going to skip. Looking at car number 3, well, let's put in 2 right away. Let's put in the normal and the force of gravity. Nothing has changed between any of the cars except for in the y direction, the force of gravity and the normal. Okay, so I got my normal here, I got my gravity here, they're all in there. That's beautiful. Okay, what other forces are acting on this object? Well, neglecting friction, because we can talk about friction, we cannot talk about friction. The idea is just to draw arrows in the direction of forces. There's a tension. This wire, this cable, this string is pulling that car. That's your free body diagram. Okay? Rule number 1, it's one object at a time. If I weren't to do it one object at a time, think about what this is going to look like. I have an arrow here, 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 I have an arrow. Oh, no arrow there. Not terribly clear. I mean, should draw it in black so you get a real good idea. So I have 1 arrow, 2 arrows, 3 arrows, 4 arrows, 5 arrows, 6 arrows, 7 arrows, 8 arrows, 9, 10, 11. Looks like crap. This tells me a lot more. This tells me a lot more. Okay? So, free body diagrams. First rule, has to be one object at a time. Second rule, all of the force vectors are coming out of the center of the object. The reason why we do that is that I can see, if I were to include the force of friction in this system, tension and the force of friction means that I have a greater force in this direction than I do in that direction. Okay? That is a free body diagram. It's probably the most important tool when it comes to forces. If you can draw it, then at least you have an understanding of what's going on. Okay? So, free body diagram.